All right, time to get this party started. So looks like we got good stream health and we are kicking bum. So welcome to this European edition of my live code. So I'm gonna try something out. Hey Spencer, I'm gonna try something out. I have a lot of people that were saying that, hey, I'm in Europe and you're always on when I'm in bed. So I'm gonna try doing it a little early. See what's going on. See if I get some of those people satisfied. And today we're going to continue our basic or our back to basics series. So last week we did, what was it? Composition, currying, and partial application. So this week we're going to do combinators. So I like combinators and I like following them up, like after I show composition and things like that, because it really gives you a chance to understand like how we can build these point-free flows or these function compositions to better, how would you say, accommodate our functional workflows. So now when I'm saying point free, I don't know if I really mentioned this before, but when I say point free, the word point, a lot of people think it has to do with the dot and like we're getting rid of dots and things like that. But not really. It comes from, and I pronounce everything wrong, so just keep that in mind. But it comes from topology, branch of mathematics. Oh, Pakistan. Hey, how's it going? Welcome. I'm glad. See, I was able to accommodate someone. Yay. It's pretty late there, right? How late is it in Pakistan right now? But the point free comes from topology, and it refers to the data that's used. So whenever we say point free, what we're referring to is free of data. So the way I like to think about it is if you were to look at an object-oriented app, object using OOP, you basically get the input from your application, and then from there, you segment all that data off into these other little objects that work together, right? So your data is pretty much partitioned and split and moved all over, and then you have these objects that interact with each other that get your final result, like render something to the screen. Oh, 9 p.m., goodness gracious. Well, we'll try to go through this really, really quick for you. But whenever we start doing these functional type things, what we do is instead of taking our data and splitting it off, we want to take our data and just run it through a series of functions or compositions that will then calculate our result. So that's why, and I believe last week, we talked about how when constructing functions, and we're going to see many examples of this, but where we actually put all of our context here. So we might have some variable x and some variable y, but the data we're actually working on comes last. And that allows us to do really neat things. Maybe data is a function, so maybe we apply x and y to data or something like that. But what this allows us to do is say let's go ahead and bring in add. And add, this is silly because add is point free anyway. Well, not really point free, but it's curried. So say we were to bring in add from require, and we'll bring it in from Lambda. What we can do now with this function is create something called 3 and 2. Okay? And what we can do with 3 and 2 is just call fn with 3 and 2. So now we have this 3 and 2 function. So if we want to call it, all we really need to do is, hold on. So if we look, we get a function back when we run that, but now we can add to it, and it gives us back a 5. So in this case, add was our data. But we could also take multiply and do that sort of thing. Multiply. And it doesn't really matter. We can take this 3 and 2 and just reuse the values of 3 and 2 over and over again. And the reason why we can do that is the way that we specify our argument order. So we might have or we call the first part of it the context. So this is the context on a binary or greater function. This is basically the context for the function. And then here, the last value is always, or the last parameter, the last argument that we take is always the actual data that we want to run on. So we need to have this layout because as we compose this stuff together, as we're going to see, we need to make sure that the data from one function becomes the input to the other function. If this data was around the other way, then we would have to do some gymnastics or some clever little acrobatics to get it to actually work properly. So we want to avoid putting data first. Basically, we always want to take all of our context first and our data last. Now, this is just a cheesy example. We'll get into more examples as we get into the combinators. So I'm not going to go too deep onto like what a combinator is or things like that. It's basically no free variables. All variables that go into these functions or these lambda expressions are bound. We don't grab anything from anywhere. They're basically pure functions. Again, not going to go into the history or things like that, except to say something like, to say something along the lines, oh, goodness gracious. I lost my train of thought. I need to not look at my watch. Okay. Combinators. Oh yeah, so they basically have no bound variables or all variables are bound. They're not anything, anything that it has to work with always comes from some inputs. Basically, check out lambda calculus if you're curious. You can look up combinators, things like that. So we're going to go over, if we look here and let's get a new Google window here. Boobity bop boop, and we will do, need to hide all of that. And what is the thing we want to look up? So we want to go Crocs, and we'll look here. So what we're going to do this week is just kind of look at the combinators that ship with Crocs. And actually what we're going to do is using just constant and substitution, we're going to build out the other ones just by using those. So it should be fun. Now, a lot of this, like, how would you say, using combinators to build other combinators, they're not very efficient, right? So I am going to show like how it would be implemented if we weren't combining combinators. And then we would just look at the combining of the combinators. And I'm hoping that we'll kind of get to see what it's like to play with composition and partial application and things like that, because it's prevalent in here. You pretty much don't specify any of your data ever. You basically put all these together. So I guess we'll start with constant. So constant, the other thing is each one of these has some sort of letter that goes along with it. I'm not going to get into the origin of that. And there's also a bird name that goes along with that. If you're curious where that comes from, there was a book that was written in the 80s called To Mock a Mockingbird. Yeah. So we're going to start with the first one, which is the constant combinator. And the constant combinator, actually, we're going to need to bring in curry from Crocs. And we're going to use our curry because instead of the Ramda curry, because of the way that it works better with these combinators. So let's create our first one, constant. And let's see here. So this is what's called the K combinator. The bird name for this is kestrel. It's a kestrel bird. And basically this takes an A, takes a B, and then gives the a back. We pretty much disregard whatever that b is, and then we give the a back. So that's why it's called constant. We'll see why here in a minute. So let's just define this. We're going to do curry, and then we'll take an we'll take an x, and then we're just not going to take anything. We're going to totally disregard whatever the second argument is, and then we're just going to return x. So you can use this in a lot of places. So for instance, say we wanted to make a default, right? Default value. And we could just take some sort of x, and we'll do if else, and we'll just say not is defined. We'll bring this stuff in. Not is defined. What would be the best way to do that? So let's not use if else. Let's use when. Sorry. And let's actually use unless so we can get rid of this not. So unless is defined, then we want to run kx. And what this is going to do, we need to bring in unless, and we need to bring in is defined. Unless and is defined. Let's just make sure we have those. And now we can do default value, and we'll just say 4. And if the next value that we get back, and actually, let's use partial application on this. So we'll do const default 4 is equal to default value, and then we'll put in 4. So now, if we call default 4, and we pass in null, we get our function back. Why did we get our function back? Oh, maybe we do need to do... and here we'll do x2x. And no. Oh, goodness gracious, because we didn't bring in if else. Boy, this is really great, isn't it? And we're still just getting our function back. Oh, duh. Because I'm calling default value. Goodness gracious. So we actually want to do default 4. Otherwise, that would have defaulted that to null. So, and here we want to do... Okay. Oh, that's interesting. So let's actually do is nil. My goodness gracious. And this will be when. So when it's nil, we want to return the other one. See, this is what happens when you go off script. So now if we put in undefined, or say we put in null, we're going to get back 4, but if we put in 10, we get back our 10. So this right here is basically what you would use this k or constant combinator for. And let's actually put in here the name of what it is. So this is our constant combinator. Here what we did was we basically created this function that's going to take some x, and then it uses this when function. We're going to get into logic and things like that next week and how to use the logic functions. But basically, if this becomes true, it's going to run this function. Otherwise, it's just going to return whatever function you give it or whatever value was passed to it. So when is actually a triple. So it takes, or a trinary function. So it takes in 3 values or 3 arguments. And basically it's going to, whenever we send in this 10, that 10 gets passed to when, and then checks to see, hey, is 10 null or nil, being whether it's nan, null, or undefined. And if it is, then it's going to call this function passing in the value. So since we don't care about that, what's going to happen is that null is going to get passed here, and it's just going to return the x. So that's a basic use of what you would use the constant combinator for. So the next combinator is a little bit tricky, and we need this one as well to be defined so we can define all the other ones. This is called the substitution. Or its bird name is the starling. So we'll take, this is a function that takes an A, then it takes a B, and then gives back a C. It's going to take that as its first argument. It takes a binary function. And then it's going to take an A to a B, and then it takes an A and gives back a C. So this is a little interesting as to what's going on here. But basically, once we provide this A, it's going to pass the A to this first function. It's also going to pass it to this second function. And then it's going to run this function and get this B and pass that as the second argument to the first function that we have. And then finally, it's going to put the result in and give us the result back of this first function. So this is called the substitution. This is really, really handy. Hey, how's it going? So let's just define this. And again, we're going to use the curry here. And this S basically just needs to take a function F, a function G, and some sort of X, or our data. And since we're curried, it's fine. It's going to take care of all that for us. But we don't know if this second function or the first function, which is binary, is going to be curried. So we're just going to curry that anyway. Then we're going to apply the X to it. That's going to be this A. And then here we just take G and then apply that A to it. So we then take this function, which is then going to result into the second parameter, or the second argument of this function. And I think that is it, except this needs to be X. So I'm not going to show a hard example right now of how to use this, because for it to be really handy, remember, we want to take our data last. So if you notice, the data for this function is A. And if you look at this function, A to B, you notice that B in this case is going to be the context, and A is the data. So we would really like a function that went from B to C. So before we can get into some really cool point-free uses for this, we need to actually have another combinator built out. So we'll show that example, I think, at the penultimate. So the penultimate one will be the one that we show the example at. So now that we have these two combinators, we can create a whole slew of combinators. We can create every single combinator here and then some. We're also going to look at two other ones. We're going to look at one called kite, and we're going to look at the eagle, but that'll be later on. They're not represented here, but it just shows different ways that you can use those. So let's make sure that everything's good. We have no errors. And then we're going to use these two combinators to build our first combinator. And this first one is going to be what's called the identity, or the I combinator. So the I combinator, its bird name is the idiot. There's a songbird called the idiot. But a lot of people have been using ibis for it because that just sounds a little nicer than idiot, right? But this is called the identity. And you'll see this. Oh, by the way, in Ramda, this constant is called always. I don't know if they have a substitution one. I haven't played with that deep. But if you're looking to use this with Ramda, this is going to be in Crocs, it's constant, but it is always inside of Ramda. Okay, so I is really easy. This is the identity function. This basically takes an A and gives back an A. And implementation of it is really, really easy. So we basically just take an X and we return the X. So that's how we would do it. And this is how I would do it if you're actually going to use it or create this in real life. But this can be used for a lot of different things. Basically, any time that you need to echo a value. I used it earlier. If you saw, I made that x to x, and then it was a problem because I wasn't using the right function. But basically, this is going to provide you pass it something, it's going to echo it back. So this is how, and just to see what that looks like, we'll just do I-45. Actually, let's do I-10. That's my favorite freeway. So if you notice, whatever I pass it, or I could pass it 10, it's just going to echo that back to me. So this is how you would implement it if you were just going to code it. But we can implement this with this series of combinators. So let's just actually keep this so we can see, or combining combinators in a specific way. So if we just take s, and remember s is a binary function, it's going to take as the first, we need it's a trinary function. We need the first one to be a binary. And if you notice, we have constant, which is a binary. So this is going to give us the constant. And it doesn't really matter what we're doing here, because remember, the constant is always going to ignore this b, right? So what's going to happen is it's going to take constant in here. This will be constant. Then it's just going to ignore whatever we pass it for its x. So that a that we pass it, it's going to ignore it. Or I'm sorry, it's not going to ignore it. This is going to apply that a. So it's basically going to echo that x back to us. And then it's going to apply this function, which ignores that, right? Because we ignore that as the second one. So this will basically apply that and just give us back. It's going to call it with this, then this, and give us back that first one, which is our identity. So we could put anything in the second one as long as it's a function, because it's going to be ignored, right? So as we see, we get the same thing back. We could put s here, but s doesn't really fit the mold because it's a trinary function and we're expecting a binary. But that's still okay. Doesn't matter. These functions can return functions, as we see. So you'll see if I even replace the second argument with s, it still works because that's ignored. But that is an example right there of how using just these two combinators, we can create this other combinator. And notice we didn't specify any data or anything like that. The data just runs through this and works as possible. So that's an example of Pointfree. So now that we have, actually, let's take a little pause here before we go on. We're going to talk about one that isn't available in Crocs, but I'm going to take a sip of coffee. Are there any other questions or anything like that before I continue? Anything you want me to answer before we go on to the other ones? Just going to wait here for a second, see if we get some questions. Oh, thanks, Alex. Alex Lewis says, this is great. Thank you. I appreciate that. All right. No questions, so I think we're moving on. And I do these pauses because people are really, really polite. Oh, wait. Really straightforward. Thank you for the background on combinators. I don't know if they're combinators or combinators. I don't know how to pronounce them, but all right. Francisco says, just trying to convince my 1-year-old son that this is great. Good luck with that. You know what works? The only way, because we partition out YouTube in our house. Like we can only watch I can only watch certain YouTube videos for a certain amount of time, and then my son gets to watch them. But if you watch the Dr. Boolean, he did that thing on YouTube with Professor Frisbee. They watch that. So like my younger kid would watch that. So I could watch that, and then he would watch the stop animation, and everybody was happy. So that's a good one. All right. So we're here on identity. So let's move on to another one. Now, This one we don't have here. It's called kite. I don't know if there's like what the name of it would be. But basically, this is just like constant, except with a little twist. We basically take an A and a B and then give the B back. So just to show you like what I'm talking about, say we have this K and we have 10 and we have 100, right? We already know that this K is always going to give us that 10. So what kite does, it would actually return the 100. And we're not going to get into the logic aspects of this now, but basically these two functions, constant in kite or Kestel in kite, they can represent true and false, because true is always going to return the first argument and false is always going to return the second argument. There's a lot of really good material out there on how to use combinators for logic. And actually, never mind. Yeah, there's just a lot of good stuff out there for that. So, but just to show you what this looks like and how, we can make other things, how we would implement this normally is we would have our little curry here, and curry would do x, and then we just give back that x, right? So that's what ki is. Now, if I go here and do ki, I get 100 back. So it returns the second argument. Totally, it's the flippity-doo-dah of the of constant here. Basically just flips the order around. So that's how you would do it with your normal implementation. But how we would do it with, how would you say, combinators? It's pretty much right there in it with the ki. So if we just do k and then we apply I, and that basically will pass the to constant, it's going to send the identity function, and then it's going to return the identity function, which is then going to, it's going to return the identity function, then it's going to ignore this, and then return the identity function there, so ready to take an argument. So when you're ready to send it an argument, it takes that argument. It basically takes the identity and scooches it over. Oh yeah, there's a lot of resources on here. Yeah, at the end, Alex, I'll be sure to link those to you. Alex says, please share if you know any more resources for applying combinators using kite and constant for true and false. It would be reversed using constant and kite. And actually, I've used this a couple times with kite, or with kite being the true value because of the whole Pointfree thing. I don't want to get into that. That's just going to derail everything, because then I have to explain how to use them and stuff like that. But I will totally link at the end of these some really good links on combinators. And if anything, the whole purpose of this is to kind of introduce you to these and kind of show, like, by using combinators to build combinators, it shows how to start thinking in a point-free manner, right? Like, we're doing all kinds of crazy gymnastics here. So I'm hoping that by explaining it and things like that, you start to build an intuition on how you could use these functions in your compositions. And it's fun to just sit around and play with these. All you need is these two, and just keep sending things to them and see how they behave. They're super fun. Anyway, so kite, we're not really going to use it. It's just good to show. It's something that you can make with identity. So, yep, exactly. So Christian said, so ki is equal to ks. Basically, if we were to take this, very good point. Very good point. So instead of just replacing this I could just put this here. Oops. I could just put this here, and it still works. Ki, 10, and 100. And this is called referential transparency. And even more so, these are called SKs. So you can have SK combinators, right? So instead of building these out, you can just use S and K to actually build these out. But what I'm doing here is just creating the new combinator and putting them there. But yeah, this is completely referential. This is referentially transparent. I can swap out either in line this actual SK combinator, or I can put in the combinator. Oops. And this is going to be SI. All right, there we go. But yeah, exactly, Kristen. Okay, so that's kite. The next one that we're going to build, now that we have, and I guess we didn't really need identity for this, but it doesn't really matter. We can create what's called the bluebird or the bee combinator. So you might know this more as, how would you say, compose, right? So this is called the bee combinator. And we'll just call this compose. And inside of here, it's actually compose B. The difference between this compose B and the compose that ships in these helpers right here is the other one is a binary function, and the way the currying and everything is set up, it's used mostly for doing combining combinators and things along those lines. So this is called compose B. Inside of Crocs. But how you would make this, or what it is it basically takes a B to a C. It takes a function that's a B to a C. Then it takes another function, which is an A to a B. And then it gives back a C. It takes an A and gives back a C. So this is just your normal function composition. It's real easy to implement. You just do const, and we'll do B is equal to, and let's curry this again, just so we can see what it looks like. So we're going to take an F and a G, and then we're going to take some sort of X, and then we're going to just do F, G, X. And basically, that's all this is, right? So say we want to create a new function called doMath or something, doMath. And we can just use B to go add 10, multiply, and we'll just do multiply 0. So now we have this doMath that whenever we send it its value, it's going to do multiply it by 0, which is always going to give a 0 back. And then it's going to add 10 to it, right? So how that works is it's going to take this first function, which is partially applied with 0. So it's now a unary function. And then once we pass it its value x, it's going to multiply x by 0 and then take the result of that and then pass that on to add 10. So if that makes sense. And just to see this in action, we'll do a little bit of doMath, and let's pass in 10, so we should get 20 back, or 10 back, sorry. Because if we want to get 20, we can change this to 1, and that'll get us our 20 back. Or if we want to double this, we can double that. Not a big deal. So let's actually put that to 5. Okay, so now this is the compose. To make sure that, or compose B, its bird name, I don't know if I said it, is the bluebird combinator. So how we would create this using just combinators. Now this one's a little tricky, okay? So what we need to do is we need to somehow, using just what we have, and we're just going to start with S, just because that makes sense. What we're going to do is we need a way to take the function on one of the parameters that we're given and then pass that and then set the other one up so it could call that, passing the result onto the other one. I'm not going to go too deep in this, kind of as a exercise for the reader. I'll let you trace this out because, oh my gosh, it's super fun. Now, if I got this right, and I might have to look this up. Crap. All right, I'm going to have to look this up. So sorry. Combinator birds. Boom. And just so you're aware, this is one of the resources. All right. So for Bluebird, it's S, and then we apply this to the first argument, and then we apply that to the second argument. Yes. See? And this will be that, I believe, right? And nope. See, I had that wrong. Did I have that wrong? So this is going to apply S to K as the first argument to S. It's going to apply S to K. And then as the second argument, we get the K. So again, I mean, you can kind of see how this is doing gymnastics. So if we take this S, which takes this binary function, remember, we need to take two values and put them together. So we're basically going to take this K and pass it this S, which is that binary function. And then it's going to be ready to not do anything, right? Because once the first thing gets applied to it, it's just going to skip over it and then return the S combinator. And then we apply the K to that as the second one. So again, I'll let you do the mental gymnastics and things like that to figure out how this works. But if you notice, we save it, and there you go. We get our 60. So another one, and that's basically compose B. We can also, like, say we want to do something else. We can compose another function with this, right? So we might have this do math. And let's bring in object of. So we will do object of. And what object of is going to do is take a string or number key, and then it's going to take a value and then return you an object with that key value pair. So what we can do here is do result is equal to, and we can just use another B, and we want to do math first, and then we want to do object of result. Right? So now if we come down here and do result, we'll see that we'll get our result inside of an object. And again, because of the point-free manipulation or the point-free application of these, doing these in a point-free manner and using partial application to make these into unary functions that are ready to take their data, we're able to just do these compositions like this. So anyway, no need to keep this around, no need to keep that around. Actually, one thing, notice this do math here. So it sucks because we're pretty much locked down to we can only add 10 and multiply 5 for this function. I mean, we could do some other things like take in that context and do stuff like that. But we have another combinator that's available to us called the E combinator or the eagle. So what the eagle does is, and this gets a little crazy too, what the eagle does is takes an A, then it takes a D as in dad, and then it returns an E. Then it takes another function, then it takes an A, then it takes another function, which takes a B, a C, and then returns a D. And then this is going to take a B, and then a C, and then gives back an E. So if we notice, there is a lot of little functions here. This is basically the eagle here. Yeah, this is the lambda for it. It takes a lot of parameters. It takes 1, 2, 3, 4, 5, 6. It takes 6 parameters there. And we can implement this. Let's just get rid of this, and we'll do const e. And I'm just going to show the implementation as I explain it, but it basically does the composition for you and all of the neat stuff. So we're going to do curry, and then we're going to take an F, an A, or an F, and let's call our data X, a Y, a G, and a Z. Then it's going to take our data, which is going to be, we'll call that X. And now this is where the really cool stuff happens. Well, I don't know how cool it is, but this is where some of the stuff happens. So what we need to do is, because these are binary functions and we don't know if they're curried or not, we need to curry this. And then remember, this is going to take a binary function. So we need to take that A first, which is going to be that. And then we need to take in our D. So here, we just do another curry. And with this curry, we're going to curry G. And this is also a binary function. So we take our Z and then it takes a C. Then we apply our data C or X. And that's what this does. So to see this in action, we're going to change this to E. So now instead of creating these functions where they're partially applied like that, we can then just come through here and replace that. And now the arguments that are going to be partially applied to them what would we put in? 10. And that gets us our 60. So it's basically just going to take this argument and then apply it to this function, this binary function. Then it's going to take this argument and then apply it to this binary function, and then it's ready to take our data. So this is another way of getting around the B. So instead of doing the partial application, you can use the eagle to do things like this. Now to see what this looks like, this is insane. This is another one of those insane ones. I mean, it's not that crazy, and we're not going to get too far into it. Replace E just so we can verify that this works. Replace that. And X. And replace that and X. Okay, so now we have that. So this one, this one's crazy. So basically, now that I have this open, I might as well use the cheat sheet instead of going from memory, right? So it's going to apply to the first one, the B combined with B and B applied to it. So it's going to apply the first argument of B with the B's applied to it. So how we represent that is we go B, and then as the first argument, we want to do B, B, and B. And that'll get us our E, I believe. So now we just do math, and we do math with 10, gets us our 60. See? So just by doing that, and again, this will be another one of the ones that you can go through and actually do the mental math on it, right? It's real fun, and it'll give you a lot of practice in understanding how function how data last can let you do some really neat stuff. What is that called? Pointfree functions. So this is another one. We don't represent this in Crocs. You'll notice that it's not in Crocs. We don't have that. But it looks like we're down to 2 more. So we have substitution, which we made. We have constant, which we made. And then we have compose. This is our B combinator, which we derived. Identity we derived. So the next thing, now that we have B, the next thing that we need to put together, because we needed B for it, is flip. Now flip is really cool. Let's get rid of this, and we'll get rid of do math. So this is the C or cardinal combinator. And what this is going to do is take a function first that takes an A and a B and then returns a C. And then it's going to take a B. Wait, is that right? Yep, it's going to take a B. Then it's going to take an A. And it's going to return a C. So if we think about this, it's basically, we can put in these little parentheses. We can say that give me a function here, and then I'm going to give you back another function that's going to flip those arguments. And this is called flip. This one is really important, and this will be the one that we can see, like, once we have this implemented, we can finally show like how to use substitution in a really cool way. All right. So now we just do const C, and the implementation of this is super duper easy. Not compose, so sorry. We want to do curry. And then here we're going to take a function f, and then we're going to take an f, and then we're going to take a B, or an A and a B. I'm sorry, an X and a Y. And then we're going to do F. And just to make sure, we want to curry this since it's a binary function. That way everything just flows. So we want to curry F, and then we're going to apply Y and X. So notice how these are flipped. We're basically, we're going to give back a function that takes the A and the B, or the B and then the A, and then we're just going to flip these parameters on them, right? So one of the ways you could see this, so one way to see this is with concat. So I want to point something out with Lambda. The reason why they do this, not all of their functions are point free, and you need to be aware. And the reason why they're not that way is a lot of times for some of them, you're using them a lot in how would you say? You're using them in reductions. Like when you call an array.reduce, you're using them as your reduction function. And those arguments are flipped. In JavaScript, we take our data first, and we take the thing that we want to, concat to it second. So if you notice here, so one of the uses for flip is if we do concat, and let's do super hot. Okay. So you see, this is not really the a point-free function, because if it was point-free, it would take the thing that needs to be concatenated to it. So for instance, this needs to be hot, and we want to concatenate super to it, right? Or we want to take super and concatenate the other one. So this way we can call this const concat hot. Right? So if we were to come here and do concat hot, like in one of our flows, we want to basically concat hot to whatever this thing is. So be aware these aren't. So here, let's do super. And notice we get hot super. So this is where flip comes into play. And also you'll notice that the concat that we use is reversed in Crocs. All of the point-free functions and all the functions that you would find here, concat, like all of these, are always set up to take their data last. So we basically, the thing we want to concat to, and actually, well, no, I guess this is fine. This is fine the way that it is. Okay. So you'll notice now, this is how we actually would want it to work, right? So we concat hot, and now we have something that's going to concat hot to any data that we give it. So say we weren't using that. Say we were using the one from Ramda. This is where flip will come into play. Because all we need to do is just take this and since we're using, that's not going to work. That's going to give us a function back. So we want to concat hot and actually, let's call this const Pointfree concat is equal to C concat. Right? So now this is going to flip the arguments there. And here we'll do C concat hot. Is equal to Pointfree concat, and we'll do hot. So now we get our super hot using theirs. But that's basically what flip does. It takes two things and then flips it. So we can actually build this with combinators as well. So here we have just a normal implementation. Oh, and you know what? Let's keep this so we have an example. So we have just our normal implementation here. We want to get rid of this. And to set this up, there's also another difference that because Ramda also has a flip, so we'll kind of show the difference between the Crocs flip and the Ramda flip. And it has to do with how the currying and all that is done. So flip is also kind of an insane one. And so it's going to be another one that you're going to have to kind of go through and see for yourself. So for the first argument, I think I got this right. Let's see if I can do it from memory. And then this is a K of K. Okay. Yes, right? So if we look at cardinal, that is on the first argument, we want to apply B and S to B. So we have B and S being applied to B. And then for the second one, we want a KK. KK. So yeah, that's basically the flip combinator. So now that we have the flip combinator, and again, with these ones, with eagle, compose, and flip, I highly recommend going back and figuring out like how these lay out, right? Very important, very cool. Well, not very important, but it'll help you kind of train your mind to think about partial application and putting these functions together. I have a lot of fun and with combinators in just for my everyday playing around. And when I was first starting to learn this stuff, it was the combinator stuff or combinator. Again, don't know how to say it. It was that logic or like the exercises and playing with those that really cemented on how to build like point-free flows and compose my data together. So if anything, it'll start building those connections if you're just starting out. Okay, anyway. So we have that, before we get into the last one, which is going to be the Thrush or apply to, I just want to show one little difference between our flip and the other flip, right? Or Crocs flip versus Ramda flip. So you'll notice when doing these, and let's do this way. So let's go flip, and then we have to do concat, and then this should still work, right? It seems kind of weird, and we'll see just by using the C that this works. See, I want to be able to just use these combinators in this way. See how it still gives me the super hot? Because all I did was I took the function that I wanted. These functions should just lay out like this and be able to apply things to them one right after the other. So with the flip that the cardinal like that we just built out, you can actually set this up. In Ramda, though, you can't do that. It's going to give you a function back. It doesn't apply things. So it's a little unnatural, but you'll end up with a lot of this code inside of like a reduction or things like that. Stuff where you have to flip stuff around, or especially in your Pointfree flows. Because remember, this is, or in your partially applied functions. Because remember, this is set up really to work on reduces. So if you need to do concatenation inside of a compose function, and you're using, like, for instance, a function like this from Ramda that is set up to use the reduce, you're going to end up with a lot of stuff like this, like compose the flip with this and then add. So it just looks really weird and is very distracting, right? Just to be aware of that. Now the flip that comes with Crocs behaves just like this. And notice you could still do this with the other one, but this allows you to partially apply things and just have a function that comes back. So just to show what I'm talking about, the normal flip that ships with Crocs works just like this C, unlike the one that Ramda has, right? So just a little side note there. So if you're ever working with Crocs, things like that, you can actually apply on these combinators that we have. It's just the way it goes. Okay, so that was Cardinal. That was, did I mention that was Cardinal? I don't remember if I did. So the last one, and this is one of my personal favorites. Oh, wait. Now that we have flip, goodness gracious, I need to show you a actual use for substitute or substitution or the starling. Because remember, if you remember from earlier, we had this, if we were talking about this, in this case, the last thing that we pass to these functions is our data, right? The last argument that all of our Pointfree functions should take is our actual data itself. Except, you know, like with constant and things like that, but we don't need any of this. So we have a function in Crocs, I think, yeah, they do have it in Ramda called assoc. I call it assoc, but I was corrected, it's assoc. So we have this assoc function. And just to see what it does, we'll go functions, helpers, and assoc. So this basically takes a string, then takes an A, then takes an object, and gives back an object. So this is just like object of here. It's going to create an object with this string, and then give it this value. And then it takes an object, and then it's going to merge that key value pair into this object. I think Ramda's the same. Ramda docs, assoc. Yep, string A, key value. So, yeah, they do the same thing there. Goodness, what would be a really cool thing? So let's create something called func. And func is basically... or FN, what should we do? So say we have a function that we want to run something on, right? Like say we want to take this object. Yep, that's what we'll do. So let's create a function that takes an object. We'll call this FN. It takes an object. Then it takes a, no, it's going to take its object last. Let's make a function that takes an object and then gives back an A, then takes an object, and then gives back an object. And we're just going to call this result. So let's call this make result. All right. And we don't really need to take in this other function. We'll just create. Let's make that. So what we want to do is say we have an object that has an A and a B on it. So we'll do calculate, right? Or just calc. And this will take the A and the B off of that object. Okay? And then it's going to, I don't know, add them together. Yep. That's all that's going to do. So this calc takes an object with A and B on it. So we'll say A number, B number. So it needs to take it in that form. And it's going to give back a number. So it basically is just a function that adds these together. So let's now create make result. And we'll use the substitution for this, or the starling for this. So we just, dinner, I can't wait to watch this once I get home. Keep it up. Oh, thank you. So what we want to do with this is we have our ASOC function, because remember, the first thing that we need is a binary function to this. So we're going to take our little ASOC here, and we need to flip, or after we apply it, we need to flip it. So we'll take ASOC. Because remember, we want to take our actual data last. And we actually, we need to curry this. And we need to bring in our function f. And then we want this stuff. All right. Okay. So now we want to flip this, and then but we want it applied with result. So now this is going to apply the key to it, and we're going to get the value because remember, this is going to take another function, which is going to be our f. Oh. And it doesn't matter. We don't need to pass our f in because that will come. All right. So now we just need to pass in calc. And that's going to be our const calc result. And here we'll do make result and apply calc. So now we have a function with calc result. And just to show you that it works, we do A 10, B 30, and we run it. And we notice that what we did was we took the A and the B, and then we added them together and then created this new function called, or this new key, and then assigned it with result. So that would work for any function. So we're doing a little trickery here, and this is kind of the neat thing about partial application is because this C is curried and it's ready to take another function, we only applied this function, which is the binary function. We applied result to it, flipped these two arguments with the cardinal here. So now we take in the object and then the A, or whatever the actual A is. And then when we call it, it passes the object to that first argument, and then it's ready to take the calculation from the second argument. See, this is the A to B. And that second argument, or that second function, is our calc function, which goes from an A to a B, And we'll notice that we go from our A, which is our object. Notice that A is the same thing in both places. It's going to end up being the object, even though the other one's flipped. Where are we at? It's going to take the A and then give back the B, which is the number. So that ends up getting applied to this B, which is now the value, this A over here. And then it applies that to the object and goes whoop and focuses it down. So this is what you can use substitution for. And it's just a way to apply, a lot of times you can use them for with functions, right? So I could say associate with and then have it take a function, or do something with and then have it take a function as its second argument, right? I don't know. There's a lot of things you could do with that. But that is an actual use case for the starling or the substitution. All right, so we can get rid of all of this now. And now that we have flip, we can do our last one. And our last one is apply to. I think that's what it's called here too. Yep, takes an A, all right. And this is our thrush or our T combinator. So it's basically going to take an A, B. It takes the arguments A, B, and then applies B, A to it. So it basically, B here is a function, A is the value, and then it flips it and applies the function B to the value A. Anyway. That's what we're going to be making now. So this is the thrush or the T combinator. And apply to, we have this, we call it apply to as well. Combinators. How long have I been doing this? About an hour. So this is pretty good. This is pretty gosh darn good. So now we have this apply to. We call it the same thing. So the thing with apply to, if you think about it, most of the time when we have functions, we have the function and we have the value. So all we do is apply that function to the value, or apply that value to the function. Now, there are many times, or there are some times that come up where we don't have the actual value yet, but we need a function, right? I'm looking at you, the breaking change of AP in Fantasyland. Ugh. Anyway, this will help you get around if you like, never mind. We won't get into that. Oh, that AP though. So sad about that. But basically, this is whenever you have the value, but you don't know what function you want to apply it to yet. You'll run into these cases a lot of times with like arrays of functions and things like that. And maybe you have a value that you want to apply to it. So this one's actually pretty gosh darn easy. Basically, it takes an A, then it takes an A to a B. And from there, it's going to give back your B. So normal functions would be, I take the function first and then do it. But this is using, it flips the script. It basically uses the function as data itself, like we saw in the very first one that we did. So we do const t, and we'll just do a little curry here just to show you like how this is implemented. So here we take our A, then we take our fn, and then we apply fn, or apply A to fn, right? So one of the ways that this works, or one of the neat things that you can do to get this to work is, say we have some data, right? We have const, and we'll call these fn's. But say this data is really just a bunch of functions, length and toUpper from Ramda. So here we'll replace this with length, and we'll replace this with toUpper. Oops. And we can get rid of the ASOC here. Don't need that. Okay, so now we have this array of functions. And we want to be able to apply this to something, right? So this is where Thrush can come in. So what we can do is take these fn's and we can map over them with the value. But the issue here is map takes a function, and we have a value super hot. So because this takes a function, I can actually apply this value, and then it's going to give me back a function, or it's going to give me back a function here that will take a function and give back a b. See how we change that around? So now we can do map, and then we just thrush super hot. And there we go. So now that gives us back another function that runs our value over each of the functions. And I'm sorry, it gives us back another array that runs our value over each of the functions in the array. So we notice that the length of super hot is 8, and we get back our 2 upper super hot. So yeah, that's basically just funds. Oops. FNS is basically just a list of functions that are different functions. So we'll just say berries. There we go. I don't want to get into the typing thing for that, but all right. So now that we know how to build this and how to use it, Asosa's Fables, I love it. Okay, now that we know how to build these out, or now that we know how to like build this from hand, let's see what we can do about building it with combinators. And this one's pretty easy. Now that we have flip, it's basically just CI, I think. I might be confusing this. Thrush is just CI. So yeah. So basically what we're going to do is, since flip takes a function and then takes the values of those, we're basically going to take the I and then flip it. And again, with this one, I'll let you figure out how that works. But if I run it, I get the same result. And just for apply to completion's sake, just to show, same thing works with apply to in Ramda, and the same thing works with apply to in Crocs. You get the same results. So yeah, that is it. That's all I got for you. Like you can see here, there are many birds. So let me just throw in some resources here into the chat. So there's that. The Combinators code is here. There is a fantasy birds. Here we go. Yep. So this is great. This doesn't have all of them, but it has the ones that are implemented in Haskell. They basically ported them over. So this doesn't really show like for instance, it doesn't show like how to build the combinator from other combinators, but it shows implementations of it. So this is a good one. Fantasy birds. Yep. The emoji game is strong. What are some other resources? The Flucher guy did a combinators. I get no respect from these people either. He won't make it on my combinators JavaScript. Yeah. See, they never include my libraries. It's always about Ramda and Sanctuary with these people. I'm just kidding. So this is this gist that he basically has. I find this useful. But the most useful thing on this whole page, yeah, this is great and all, other than it doesn't have Crocs. The The only thing that's really, or the thing that's really, really good on this is this right here. These two videos are amazing. Yeah. So basically, this does the lambda calculus, talks about the true false stuff. And then this talks about using numbers and church encodings. Yes. Okay. Those are all the resources I have. You can search for all kinds of things. Ooh, fixed points. Nope, can't watch that now. Yeah. So those are all the resources that I've kind of gathered from or looked at and did things with. Yeah. That's pretty much all I got. Next week, I'm going to try this the 9 o'clock time again. We had a pretty good turnout. I'm curious how many of the people were actually people I worked with, though. And how many, it looks like we got a few of the people that wanted me to switch to a more European-friendly time. So good, as long as we've accommodated them. But next week, I'm going to try the 9 o'clock again, 9 o'clock my time in the morning, basically the same time we did here. But we're going to go over logical functions and how to use these functions for doing logic in your app. Way to capture disjunction and things like that. No bubs, no trubs. Yeah, so that's all I have. If you guys have any questions or anything, feel free to leave stuff in the comments, like, subscribe, blah, blah, blah. Oh, good. Gnarly? How do you spell your name? Gnarly? Or pronounce, sorry. I see how to spell it. But good. I'm glad this works out well for you. What time is it there for you? All right. Cool. I will take your answer offline. Yeah, so I will see you next week. Thanks so much for joining me. I hope this was helpful for some. And have a wonderful day. Oh, see, I didn't have my button ready. All right, let's start that again. Blah, 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 like, subscribe, blah, blah, blah. Have a wonderful day.